So thanks for having me. Again, it's been a while, but I was here a few years ago, and it was a great visit. And now it's shorter visit, but it's been great. And thanks to Sarah for hosting. So this is one of the talks I give as part of my lecture tour. As most of the work I present, it's team based, highly collaborative. So this one, I want to make sure I acknowledge the people I work with. But amongst all the work I've done and the talks I'm giving this year, this is one where I am truly the messenger, right? In some of the other talks I give, I'm more directly involved. This one, I'm of course involved, but really this was led by my colleague Tom Gleason. And my contribution, was through my former PhD student, Kevin Beefus. I'm gonna point out his work. And then one part was led by Scott Giseco, and another part was led by Elko Lauendijk. So I want to make sure it's clear to everybody that this was work done by really different people, and I just kind of put things together. As Sarah mentioned, I'm visiting you today as actually not the Birdsall-Dries lecturer, but the Birdsall-Dries and Lamoureux lecturer, which is kind of new and most people don't recognize this. It is supported by the GSA Hydrogeology Division, and of course, my institution is also providing extra support. But a little bit of history on the Birdsall-Dries lecture. It started off as the Birdsall Lecture in 1978, named after the USGS hydrologist John Birdsall. And then in 1992, Shirley Dries, who was a professor at the University of California in Santa Cruz, she was the Birdsall Lecturer, but tragically was killed in a car accident a year after that. So to honor her legacy and her memory, it became the Birdsall-Dries Lecture. Since 2016, the family and estate really of Phil and Bunny Lamoureux donated extra funds for the lecturer to go overseas. So basically you have a budget, you can use it however you want, but you want to make sure that the Birdsall-Dries lecturer can go overseas. And the reason for that was, based on what I read, is Phil Lamoureux did a lot of consulting. He owned his own company with his name, but he was doing a lot of consulting work in developing countries overseas. So he wanted to make sure that the Birdsall-Dries lecturer has an international footprint because he was passionate about that. So if I'm overseas, I'm the Lamoureux International Distinguished Lecturer. If I forget my passport, I'm the Birdsall-Dries lecturer. But I like to just call it the Birdsall-Dries and Lamoureux lectureship, even though the GSA Hydro Division doesn't call it that way, but it's literally the same thing, right? And I just I send my receipts to different accounts, one for domestic, one for international. Okay, so let's talk about groundwater a little bit, just to remind everybody. I reckon not everybody thinks about groundwater all the time, but how much we depend on groundwater. So this is out of Petrodol's work, but approximately 1/3 of all the water we use is from groundwater. And some people would say it's probably higher than that. I don't know if I agree or disagree. Close to half of water used for irrigation, i.e. our food, right? Food production comes from groundwater. And the interesting part with this is when you pull water out of the ground, some of it goes back into the ground and becomes part of the water cycle, just keeps on cycling. But some of it, people think up to 1/5 is permanently removed. It's depleting the aquifers, right? And to show the level of stress of these aquifers, Tom Gleason actually came up with this idea, simple idea, but at the time a bit challenging to implement because of needing the data, of the groundwater footprint of any given aquifer. So pick your favorite aquifer, and you can just make a ratio of how much water is being extracted, use, divided by how much water should be going in naturally through recharge. And if you have a ratio of 1, do you think that's a good thing or bad thing? I think it's kind of messed up already. If you're at a ratio of 1, basically you've depleted recharge, right? Because you're basically saying recharge is now 0 because we're going to use all the recharge. So I think 1 is already an issue. And if you look at his map of major aquifers on Earth, blue is less than 1, gray is greater than 1, and this red is 20. And he visualized it this way too, like this is the actual area of this aquifer, North Arabian aquifer. This is the ratio of this area to this area is the groundwater footprint. So it just tells you how stressed some of these aquifers are. So a lot of them are getting permanently depleted, essentially. And where does that water ultimately end up? If we pull groundwater out and it doesn't go back to the ground, where do you think it all ends up? Atmosphere, which all ends up where? I mean, we're not filling up the atmosphere. We're not creating more humidity. Ultimately, ocean, most likely, right? It rains out. It's a water cycle, but actually a big chunk of all the rain that falls into the ocean. And those that fall on land, some of that will become runoff, which enters rivers, which also goes to the ocean. So what's being shown here, actually two different papers, but total cumulative groundwater depletion in volume over the last half century, but there's wildly differing estimates. So there's uncertainty. But if you convert this to equivalent sea level rise, you're talking 2 to 6 centimeters of sea level rise, just because of moving groundwater from land to the ocean. That's a lot of water that we're moving around and we're depleting. And when you think about, again, managing something sustainably, say water resources, or even, let's put it this way, right? Your bank account. If you don't want to go bankrupt, you don't want to be withdrawing more than your deposits, right? So a balance between inflow and outflow. And of course, if you have more inflow, your paycheck is larger than your spending, then your storage should go up. And the opposite is the bad problem. If you're withdrawing more than your paycheck, then storage goes down. And of course, we know at steady state, if you're living paycheck to paycheck, you're not getting richer or poorer. However, this would be your typical mass balance, inputs minus outputs equals changes in storage. But what we set out to do, the group of people, is, okay, let's say you withdraw $10 today. You withdrew $10, and somebody deposited $20. Or maybe even you can flip it, right? So you withdrew 20, somebody deposited 10, so you're down 10. But do you know if you're bankrupt or not? Do you know if you're a millionaire or not? Because if you have Elon Musk's bank account, that imbalance doesn't matter. And that's what we set out to do. It's like, well, we don't think about that because this equation, mass balance, gives you change in storage. It doesn't give you storage. So what we wanted to address is, well, we wanted to know the total water in the system, right? Because if you're thinking about available water, you also want to know this too, not just the imbalance, not just the change in water storage through time. And of course, let's not forget, we're not going to address this in this talk, but you always want to know too whether the water is usable for whatever purpose, right? You want to know how big your bank account is, but the water quality of that bank account of water. So what we're going to answer today is the first one that I alluded to: how much groundwater is stored on Earth? And then the second one, now it goes back to a broader question, right? Is groundwater a renewable resource or not, right? And let's make it simple, right? Is oil a renewable resource or not? No, and we call it a fossil fuel, right? And now groundwater is tricky. Is groundwater renewable or is groundwater fossil? So we're gonna try and address some of that. And finally, this is more, I would say, an Earth system perspective. How fast does groundwater naturally turn over or get replenished over geologic timescale? So we'll do this one by one. So how much groundwater is stored on Earth? Let's go back. If you just wanted to know how much groundwater is beneath your feet, everywhere, there's only one measurement or one parameter you have to measure, and that's the answer. And what is that parameter? This is interactive. The students can answer, and the professor should control themselves. There is only one physical measurement you have to do to figure out how much groundwater is underneath us right now. And you'll be close enough. You won't be exact, but you'll be close enough. All the students are looking away. It's easy to identify the students. Porosity, right? Who said porosity? There you go. It's just an exercise in measuring porosity. And if you make the naive assumption, but you can't do anything else, that all the pores are water filled, you already know how much groundwater is underneath you, okay? And that's what we set out to do. And it turns out, well, prior to this, Tom Gleason had developed a global porosity map. The way you get this, these are not based on measurements. Basically, how he did this is Take a geologic map. This area has sandstone. What's the average porosity of sandstone? Give it that number to all the sandstones on Earth. And what's the average porosity of basalt? Give it that porosity, right? That's what he did. So he turned a geologic map into a porosity map just based on tabulated values. So this is the porosity map on the surface. This is on the surface. But what should, in the absence of three-dimensional geologic maps and three-dimensional knowledge, what can you at least hypothesize or conceptualize in terms of how porosity changes with depth? Is it uniform? Like, can we extend this to a kilometer underground? It decreases because of what? Pressure, which leads to compaction, right? And what else, right? There's another process that would decrease porosity. How do you turn sediment into rock? Yeah, lithification, cementation, right? That's how you get sandstone from sand. So, but both of these lead to porosity decrease with depth. So this is what Elko did. Elko Lauwendijk, who's now at the University of Bergen, he was a postdoc working with Tom at this time, but he basically compiled reports from the oil industry, because they're the ones who are constantly drilling deep, getting core samples, and they really care about porosity because that's how they make money, right? Their money comes from porosity, where all the oil reservoirs are, that's where the oil is stored. So he compiled this 30,000 samples for siliciclastic formations, 10,000 for carbonate. And this is what he found compiling everything. Siliciclastic rocks from the surface going down to 2 kilometers, you can see the porosity changing from a little bit more than 20% to a little bit less than under 20%, with a broad uncertainty. Of course, there's variability and heterogeneity. But that's your typical porosity profile or decay curve. For carbonate rocks, you have the same thing here. Now going from a little bit less than 20 to close to 10, so there's actually more decrease. But you can fit a curve to this, and in fact, it should be an exponential curve. If you take a geotechnical engineering class, that's what compaction does. It's an exponential decrease in porosity. And we have a name for that. This is actually called Athy's law, where porosity as a function of depth z is porosity at the surface times some exponential decay. And it turns out the compaction is a mechanical property, right? Some rocks are stiff, some rocks are compressible. And this is compressibility. So if you've taken a groundwater class from Professor Solomon, that's the compressibility of aquifers, because that's how well we can squish these rocks. Or you can just fit it yourself as the exponent, or you can just take it out of a table. But this is what Elko found. Carbonate siliciclastic, this is the N naught, and this is that beta. And we just assumed if you have volcanic rocks and crystalline rocks, probably metamorphic, they're not that elastic. No, we just assume they're uniform. And from that, now you can calculate based on starting at the surface. This is the proportion of siliciclastic, carbonate, volcanic, and crystalline rocks at the surface. And you just decay their proportions with depth based on the equation. You can actually get the distribution of porosity as you get deeper and apportion it to the different rock types. And you fill up that porosity with water. So here we're ignoring the soil or vado zone. You get the amount of water-filled pores on Earth. And since we know the area for each of these rock types, you multiply depth versus area, you get volume. So from this is basically the porosity, the total pore space in the upper 2 kilometers of Earth. And if you just say this is filled with water, then this is the total volume of groundwater in the first 2 kilometers. 22 million cubic kilometers. And prior to this, which is why we set out on this work, there's been some other numbers in textbooks, and we dug up what these are. They're literally back of the envelope calculations, like a quarter page, where basically somebody said, I know the area of Earth, land mass, and I'm going to assume 1 porosity, or maybe 2 layers. But, I mean, what is the range of porosity? Is it 0 to 1? So you're not going to be off by an order of magnitude, which is why we're kind of within the same order of magnitude, right? But now we're a bit more data-driven. So I think this is more or less the total volume of groundwater on Earth in the first 2 kilometers. Now the question is, how much of this is modern or renewable versus how much of it is fossil. And the tricky part here is, let's actually step back a little bit. How would you define a renewable resource versus a fossil resource? What's the boundary? What's the criterion? So, but that's supply, right? That's how much there is. Time scale, and you actually said human time scale, right? Why do we know oil is fossil? Let's say we even have 100 times the oil that we have, or 1,000,000 times. We would still call it fossil and not renewable, right? Because it doesn't generate in our lifetimes in the time scale we care about. It's millions of years to produce oil, right? And now groundwater, so why is solar renewable? Because it renews every minute or every second, right? Because you've got radiation happening all the time. Okay, but this becomes tricky because if you look at the age of groundwater, so this is age, and this is out of, actually I don't know what it's from. It's somewhere I stole from the internet. But looking at groundwater age, 0 to 10,000 years. Is it renewable? What is renewable in this time frame? And is it really just 0 to 10,000 years? So this was tricky. So what we decided to do is we're going to just borrow the concept of sustainability because we don't know what the time frame is that we should use, right? Should we use 1,000 years, 10,000 years, 50,000 years for renewable? So we use the definition of sustainability, which is anything that's sustainable meets the needs of the present generation without compromising future generations, right? Meaning your children, grandchildren, great-grandchildren should have access to the same resource. It becomes a generational timescale. That's great, right? It makes sense for sustainability. Sustainable, not renewable. So that's the point. Sustainable is not renewable because you can make oil sustainable if we use it at, say, 0.01% of how we use it right now. It can probably sustain generations more, but it's still not renewable. So don't confuse this. I just want to make sure you're not confusing it, but we're borrowing the idea of sustainability because it brings the idea of generations as a timescale. So now the next question is, what is a generation of an organism like Homo sapiens? How do you define a generation? And I picked this up from grad school because my neighbor was an entomologist looking at resistance of some bugs to some pesticide. And he was like, yeah, I'd kill generations of bugs. And I know after so many generations, they've developed this resistance, right? So how would we define a human generation? Precisely. Actually, when the next generation is born, and one more thing, right? Exactly. So it's from birth to death, right? So we looked at that, and this is global. So average age, obviously not true in developed countries, including the US. Average age of when a parent gets their first child is 25 years. And life expectancy is 71 years for the world, right? And in Texas, this was in 2015, is 78.5. And I know everything dropped during COVID, right? But it's 71, 78.5. And we know men die 2 years on average ahead of women. You can guess why, probably life decisions. But you can now just say 25 to 75. I like that number, right? Because that is 50 years. Nice and round. So we decided, our group, very subjectively, that modern groundwater is going to be groundwater that's 50 years or younger. And even a century and younger, we call it young. Not technical terms, but we decided to just have these quantitative delineations. Modern is 50 years or younger. But there's an issue, right? So if you look at an aquifer, it doesn't look like a bucket. This is a typical aquifer from recharge to discharge. So if we just zoom at that, simplify it, this is the flow field you would get. Recharge flow lines, discharge flow lines. And if we release particles at the same time, they recharge at the same time. By the time they come out, they already have a broad distribution of age for this simplest of flow fields, which means this is the norm. everywhere you go because of how groundwater flows regionally. So now, well, that's tricky. How do we know if it's modern or fossil when you have this problem of smearing age all the time? So first off, we wanted to use tracers. So this is Scott's work. So we're going to do it empirically through observations, where it turns out when we did this work, it was around 2010 when we started doing it. This is tritium concentrations in water samples going back to the 1930s from basically expensive wine, old wine, right? This is logarithmic. So this is the amount of tritium or concentration of tritium. Logarithmic. So basically nothing is the background. And of course, the tritium is part of the hydrogen bomb. And it was detonated and got into the atmosphere, became part of the water molecule, which is now, it's a tracer of around this time, because if you find, and there's naturally occurring tritium, but it's very small, right, as the background suggests. But it peaked in 1975, so peak of the Cold War, and then there were moratoriums on bomb testing. It started going down again logarithmically. So if you have high tritium, you basically say water is probably somewhere around here in terms of age, which is about 50 years compared to 2010 when we started doing this work. So that was beautiful for us at the time. So what Scott Giesecke then did is he compiled literature information. So looked at all the data that's ever been published that reported tritium levels. But what he was precisely looking for too is he wanted to know what depths they were from. That was crucial. So he was compiling information on tritium concentrations on groundwater samples and depths. And he ended up getting 4,000 data points from 55 countries. And from that now, what he ended up calculating is the ratio of a given water sample that's modern or younger, 50 years or younger. Because there's no such thing as a pure water sample, right? They're all mixed. Waters just mix in the surface and in the subsurface. And to do that, now you need the background, old tritium. And this is what the sample is reported from the lab. But what is modern? Given what I just told you, it ramped up and it went down. At the time when we were doing this paper got published. It was perfect for us. So this is tritium in precipitation from 1960s to 2005. So now you can say, well, if I'm at this location, my tritium would have varied from this concentration in that color to, where was it, that concentration. And you can just use that as your error bar. And that's what Scott did, right? So this modern changes. So we have error bars around this. But he calculated then the ratio of modern water for a given groundwater sample as a function of depth, because you know the depths of the samples. And this is what he compiled. This is now the vertical profile to 2 kilometers of all the water samples he collected. I think this is the median, and this is the interquartile range, and that's the discrete data. And here you can see that, so 100% modern would be everything is 50 years or younger. So some samples actually hit that, but on average it's right about here. And it's more or less gone, if you look at the median, or even if you look at the error bar, 200 to, say, 600 meters. You don't have much modern, but notice we're still getting hits as you get deeper, okay? But now we have a sense of where the modern water is. The beauty of this is we have the porosity data. So you multiply this profile by the porosity data, which is the volume of water at any given depth. You can calculate the ratio that's modern for Earth. Does that make sense? Okay. So what he got was 1.3. Remember what the total was? 22. So that leads us to conclude that 6% of the total groundwater is modern or younger. But we're honest about the uncertainty here, 1 to 17% because of the spread in this data. But we have a sense now of how much is modern. 1.3 million cubic kilometers. We're going to look at this from a different perspective now. So this was work done by Kevin Beefus for a part of his PhD. He's now at the University of Arkansas. But you can do these so-called age models. So remember this groundwater flow field? And now you can calculate the age anywhere along this flow field if you assume everything starts at age 0 and they age with time. Just like, I'm a second older now, I'm a second older now, I'm a second older now. And you just say that when the water molecules move. They accumulate age at a unit of time per time. And when you do that, you can easily create these plots. So these are actually model generated. These are calculations. This is not a cartoon. And you can see the age in this particular case, 0 to more than 5 centuries. And you can easily find the 50-year contour, which is modern. So now you know that's the modern groundwater, that portion. And we know the porosity distribution. You can now, and the rest we'll just say for now it's fossil or non-renewable. But we wanted to do this for many places around the world. So this is just for context. This is how you do this. You do a typical groundwater flow equation, and then you add this, what's called HS mass transport equation, which is literally one line of code in a typical transport model, and you get that colored plot that I showed you. But what we wanted to do is, so we have to solve these two equations. So this is an example of that again, okay? And we're just gonna look at a few specific cases. So this is an aquifer, 5 kilometers long, 1 kilometer deep, and with this inclination or gradient in the water table. And you can see in this case, and with these properties, right, with permeability, anisotropy, and we let the permeability and porosity decay with depth as we had mapped. And you can see, yeah, there's young water here, but what you can do, boom, boom, boom. What I did there is I made the groundwater table steeper, which causes faster flow, right? Just like if you roll a ball downhill, the steeper the hill, the faster the ball goes down. So now groundwater is flowing faster, and look at the age. Everything is younger now because the flow is faster. And now I've just changed the anisotropy here, meaning horizontal flow is stronger. And you can do the same exercise. So it's just showing, yeah, you get a lot of insight just from these toy models. And now what I did here is I just changed the permeability by an order of magnitude, lower. Now it's like mostly old water. But again, if I push this water faster, but now it's not turning blue, there's still old water here. And so on and so forth, right? But this was 16 just toy models, and we actually published this because just to show this thing can be insightful, and you can see the sensitivity to these parameters. What we wanted to do is, so it's the same schematic here. We wanted to apply this for all aquifers on Earth. We're going to apply the same conceptual model and approach. But that means you need to know how wide this is, going from flow divide to discharge point. So you need the basin width. And what do you think these flow divides correspond to in a landscape like this, the Amazon, for example? What's that? Mountains, ridges, right? And then where they come out would be the rivers or the valleys. So what we ended up doing is you can just take any watershed, do the analysis in whatever spatial software you use, and tell it, give me the average distance between a ridge and a valley. And that would be representing this whole region. Okay, that's wrong, but it's an approximation. And you need to know the slope of the water table, the head gradient. Well, at about the same time when we started doing this work, Ing van Reinfelder published a water table map for the world. So now we can get the slopes anywhere. And then, of course, we know the porosity at the surface and how it changes with depth. But what I didn't tell you, in the same paper, Tom Gleason also mapped permeability or hydraulic conductivity. Same thing. If you have sandstone, this is a typical permeability of sandstone. So we had everything that we need. And basically, we were going to apply it to every point on Earth that we could. And the data that we use is this so-called hydrosheds data set. So we're doing it per watershed, not per aquifer, to be more precise. Like, this is the Amazon watershed, but it has sub-watersheds in it at whatever resolution you want. But if you look at the hydrosheds data set, it broke the world into about 1 million watersheds, these elementary units. The problem is the modeling is straightforward, but some models, depending on parameter combinations, will take seconds to finish on a computer. Some actually took weeks. And if you're a PhD student and you're running 1 million models and you don't know how many of those models will take weeks, that's not promising, right? So what my student Kevin did is basically, let's just bin all these watersheds and to make it simpler, like just 49 half widths and 33 water table gradients, and then say 9 different rock types. Basically, we created a lookup table of just 40,000 watersheds, and we assigned the 1 million watersheds to your closest watershed in the parameter space. And those 40,000, some 40,000 model runs would actually take more than a month still on a powerful desktop. And if, of course, you're a grad student, you never get things correct the first time, right? So there'd be a line of code that's kind of messed up. So it'd be like, okay, it's gonna, I don't know where the problem is, and it's another month. So it's basically, it was a year of messing with this for Kevin until he felt that it was good. So basically, yeah, we have 40,000 of these. Remember, that's the contour, that's 50 years. And the way he would analyze this is integrate this volume, put it on top, and there's 2 metrics you can look at. What's the average depth to where this boundary would be in the subsurface of 50 years or younger? Or you can say, you can pond all that water on top, just like 5 inches of rain, you have 5 inches of rain on this watershed. So you can say there's 5 inches of 50-year or younger water. That's what he did. So these are the metrics, right? The effective depth, which I'm not going to talk about, but it's really more this. This is more intuitive, how much water there is if it were ponded on the surface. So essentially, we would assign it to each watershed, and we'll get a map like this. And this is the important part, because we got a lot of pushback on this work, rightfully so. You want to view the results with beer goggles. It's a hazy picture of things, right? And of course, with beer goggles, the more I drink, the better you look. So maybe our maps look better the more you drink. This is not the point. You do not interrogate these maps with a microscope. And if you have a local problem, you should be looking at local models, not global models. Really, a better way to view this would be the map I'm going to show you is a mosaic, right? Of course, you all recognize what this is. But is that an ear? No, right? But you still see the big picture. You understand what it is. That's the point of what I'm going to show you. But to the extent that even my the group, a subgroup of us and our co-authors wrote a disclaimer saying, do not misinterpret what we just presented, i.e. groundwater age, okay? And in particular, do not misinterpret it as meaning sustainability. It's just the amount of water that's 50 years or younger, period. And there's error with that because we created this map. Where every watershed on Earth, you can now look at the thickness of 50-year-old or younger groundwater. And since we have an area and a thickness, we can calculate the volume. The total volume of all these blues is 0.35 million cubic kilometers. Remember what it was based on tritium? 1 point something, right? 1.3. And with our uncertainty, again, we embrace uncertainty, they overlap. So 2 absolutely different techniques give us essentially the same number. So we're pretty happy about this. Am I going to say this aquifer really has that much? Probably not, right? If you really wanted to do that, again, build a local model to address your problems. Don't use this global. Remember all the simplification and approximation we had to go through to get to this. Okay, so now, yeah, total volume is 22.6 million from the porosity analysis. From the tritium, we got this volume. And from the modeling of age distributions, we got this volume. So they're lining up nicely. How much is that? This is that volume I told you about. This is the total, 22 million cubic kilometers. This is the 50-year or younger. We even show it for the other bins, 25, 75, 100. So it looks tiny compared to total volume. And this is to scale. And my colleague Tom Gleason was adamant we use a proper water drop, not the fake teardrop looking one, which doesn't exist in nature. But these are other reservoirs of water, while this modern groundwater still trumps all these other reservoirs. It's still a big amount of water. Okay, I'm not going to read this in the interest of time, but this is what I just told you. Because now we're going to go to the next question. How much is fossil? And this was also work done by Scott Giesecke, but now he looked for a tracer that gives you the old fraction, which is the carbon isotopes. And same thing, he compiled information, papers specifically that report carbon 12, 13, and 14, probably for some of the corrections in the calculations. But we also decided to pick a time frame. So in this case, we decided, of course, Holocene is water that's 11,700 years or younger. And fossil is anything older than Holocene is what we decided. 11,700 years or older. And I don't know what Scott's reason is, but earlier we had the ratio of modern, which was R, and now it's fraction of fossil, which is F. But it's the same thing. It's the proportion of a water sample that's now Holocene or older. And same thing, you need to get the background and so on. And he was able to get more than 6,000 samples from the literature, also with depth. That was the cool part. He was always looking for depth. And this is what he ended up finding. This was what I showed you, modern, and this is fossil, which is nice because you can see how complementary they are. So you can have fossil groundwater on the surface, but not a lot of it. And of course, as you get deeper, this time to a kilometer depth, as you get deeper, at some point, you're mostly just fossil groundwater. 11,700 years or older. This is a composite for the whole world, right? Not for any given aquifer. And from this, with the uncertainty, and again, multiplying it by the porosity, Scott was able to show that roughly 2/3 of total groundwater on Earth is fossil. And I said about 5% is modern, but that's a different scale because that's 50 years or younger. This one is 11,700 years or older. Okay, so we kind of have a sense now how much is fossil. And now we're going to look at it from a different perspective. How fast does this water naturally turn over? But we're going to do, again, extreme simplifications to be able to do global calculations. What we do here now is these aquifers bounded by really their watershed boundaries, not the aquifer boundaries, we turn all these aquifers into a bucket, a box. And we empty the box, but we start the emptiness at the last glacial maximum, so some 23,000 years ago. Because the world is more complicated before the LGM, and when things are frozen, groundwater is complicated. And there's another reason that I'm going to show you. And then what we're going to do is we're going to fill this box up from recharge, the amount of rainfall that infiltrates and reaches the aquifer. And of course, now you do this through time, right? Let's say, okay, you start from the LGM to 20,000 years ago, so some 3,000 years. That's how much got recharged. And then you just assume some piston flow. So 20 to 15,000, that's how much recharge. 15 to 10,000, that's how much recharge. And so on and so forth until you actually fill this up. So in this case, it took from the LGM to 5,000 years to fill it up, which tells you how long did it take to fill it up. If LGM is, say, 23 for simplicity, to 15, 8,000 years. So this aquifer has a turnover time of 8,000 years. That's how long it takes to flush it. What's also interesting, if you move this analysis in time, of course, again, this doesn't happen because we don't get piston flow and aquifers are not boxes. But you can still get a sense of, now the old water has left the system, and this is the age of the waters that are resident at this given point in time, especially if you bring it all the way to the present. Okay. So, but in order to do the analysis for a given aquifer, we need to know groundwater storage volume. Do we know that? Yes, from our porosity calculations. Well, do we know recharge through time? This was the linchpin. We have a hard enough time quantifying modern recharge. We can quantify it, but there's uncertainty. And people still argue about it. People argue about it their entire careers. how much recharge there is in a given aquifer. And now we have to do it through time. So the groundwater volume, I told you about this, we know this already. But it turns out there's two competing maps, both from Europe, from Petrodol's group and Inge de Graaf from Utrecht, where this is their best estimate, model-based too, of recharge, modern recharge, or today's recharge on Earth. But as we were doing this work, again, we did this work around 2013, this paper came out where climate scientists ran climate models going back from the LG 20,000 years to present, which was a massive effort. These were running on big computers in NCAR. But these model outputs gave us rainfall. But it's not recharge, right? But would you hypothesize that there's a relationship between rainfall and recharge? Sure, right? The wetter the place is, the more recharge you get. Salt Lake City, dry, probably little to no recharge. So there's this linear correlation between recharge and rainfall. And that's what we ended up doing. My student just made linear correlations between rainfall and recharge. And we just said this is fixed. And now we can convert any rainfall to a recharge value. So this is now the recharge maps from the LGM to 1990, for example. But this is really a rainfall map multiplied by some factor to turn it to recharge. Okay, and since we have two recharge data, we looked at both these papers that got published. And now we can do this. Now we can get an aquifer, say an aquifer in Austin. I don't know what it is, probably some carbonate aquifer there, part of the Edwards Trinity. And now you can say from 23,000 years ago, you start filling up the aquifer with recharge. And at some point, you fill it up, you fill it up by one volume of the aquifer. So this is number of turnovers. And that's the time it takes to fill it up. That's the turnover time. But since you can fill it up many times over, you can go above one. And now you can say for this aquifer, since the LGM, it has filled up 9.3 times over. That's how much volume. So that means the rest should have been discharging, because you're not going to explode the aquifer, right? It's not like a balloon that will expand. So now we have two metrics: the turnover time, the time it takes to fill it up one time, and the number of turnovers. So this is the turnover time now for Earth. And notice you can see some turnover in less than 1,000 years. And it correlates with climate, Amazon, Congo, Southeast Asia, fast turnovers, wet areas. And the areas that are arid, turnover times exceed the data, in fact, exceed 20,000 years, because that's our maximum. The Western US, Sahara, Australia is pretty dry, right? Atacama and the deserts of South America, and so on. But if you just look at global averages, really most of the groundwater, the aquifers on Earth have turnover on average 5 times. And 1/3 of the global area has not turned over. And this is another way of viewing that. This is the number of turnovers. So you can really, and this is log. So this is one turnover, log of 0, or log of 1 is 0. And you can see some aquifers have turned over many times in wet areas, and some have turned over 0.1, 0.02, 0.00, or 0.01, 0.001 times. Very dry areas, because you haven't really had the time to fill them up, really, if you imagine filling them up. So this is a composite of that data. You can think of this as a histogram, cumulative histogram. Global proportion, so it should go 0 to 100%. But notice, so it's like if you're familiar with grain size distribution diagrams, it kind of looks like that, right? But let me interpret a few things for you. For example, this is the Holocene, 11,700 years. And this is telling us between 0.6 and 0.8, but this is 0.65. So it's telling us 65% of groundwater stored that's been recharged is Holocene or younger. And guess what? It lines up with the carbon data, right, that Scott did, about 2/3. And it told us, notice there's this gap. This is about 0.7. That's 0.7 right there. This should go to 100, right? But we can't go to 100 because the older stuff, we can't analyze it because we top out at 23,000. So it's telling us 28% is older than 23,000 years. And really about half, if we now look at 50.5, so half of groundwater stored right now has a flushing time or turnover time of 3,500 years. And this one, I think, is intuitive. So let's go to this. This is the conclusions from that. But let's look at this one. About half of all groundwater on Earth, the aquifers, have a turnover time of 3,500 years. Well, what's the turnover time or residence time of the oceans? Of Earth's oceans. So another way to view it is, if you emptied all the ocean basins and start filling it up with all the river discharge, how long will it take to refill up the ocean? Anybody know? 1,000,000 years, a year, 2 weeks, 10 million? Any guesses from the students? Come on. 1,000? 500 what? You need units, come on. You can't say 500 dimensionless. I think it's about 2,000 to 3,000 years. So this, I think the value of this work, so this is not a water resource thing, it's an Earth system perspective thing, right? It showed to us that these aquifers are getting flushed and connect with the rest of the Earth system, hydrologic system, at the same scale as the oceans, which I don't know if you would have thought that, Kip. Yes? Well, you're the expert. Yeah, no, but I mean for the groundwater, right? So it tells us the groundwater is, these groundwater reservoirs are an active part of Earth, even through these thousands of years timescale, right? And we know we put CO2 in the atmosphere, it's mostly going to the ocean. Of course, there's chemistry involved there with gas solubility. But this is telling us, yeah, the aquifers will respond at the same rate. Whatever perturbation you do to the Earth system, it's responding at the same time scale as the oceans, which to me, was a nice new perspective. So this is what I was trying to show. Actually, there you go. We're all wrong. 4,000 years. But yeah, there's a range too. But this is what's interesting, and most people don't know this, but for the students, the atmosphere is an incredibly fast conveyor belt in the water cycle. Just 2 weeks is the residence time. That's why, yeah, you release tritium in the atmosphere, it makes it around Earth in 2 weeks. That's why it's been a nice tracer, so to speak. But again, it gives you a sense of these reservoirs in the water cycle, right? Even though this shows more than 10,000 years and a lot of it is older, about half of it is still within the range of the oceans. Okay, so we think there's more applications for this information recreated. For example, we talked about water resources for modern or renewable, but the flip side to this is if you know how much is modern or renewable in its distribution, it also tells you how much you can possibly contaminate from human activities, right? So you can turn that into a vulnerability map or perspective. If you have mostly young water, then you know it's easy to screw up that water, right? Or your water in your aquifer. From a more scientific perspective, I think these age maps that we created, we actually have the full distributions I hope they're still intact in external hard drives somewhere. We haven't put it in the cloud, but it can tell you the extent of water rock interactions, right? Because you know, okay, this aquifer has this percent of this age. And if you can just look at some kinetic reaction or even equilibrium reaction, you don't know how, you can tell how far or close or what proportion of equilibrium you've reached. For example, how much quartz has dissolved in this aquifer. But if you know the age of that water, you can get a sense of how much. And we never made it that far. We were thinking about it. Another important context for this is waste sequestration, right? I think in Europe, they require their nuclear waste repositories to stay intact for, I think, 1,000,000 years. And I think they connected it to the half-life of uranium, which how do you even do that as a scientist to say this is the risk to 1,000,000 years? But in terms of a few thousand years, for these different nuclides, that's millions. This is log, right? You can at least get a sense of, then go to where there's old groundwater at the very least, if you're worried about your groundwater or you know that groundwater is barely moving. Okay. With that, yeah, I want to thank the people who really did this work. And since I'm on a lecture tour, I want to give a shout out to the family because I'm away a lot. And of course, they've supported me throughout all this time. But I want to thank them too. And hopefully you guys have questions. Thank you. Yes, Skip.
Yes.
Mm-hmm. Yeah.
Old aquifers or almost everything.
Yeah. Yeah. Yeah.
Wondering if you thought about, what fraction of this modern water has been impacted.
Mm-hmm.
Some of the.
Yeah. We have not. I have not personally. What I've really thought about is the water rock interaction bit because they report calcium, magnesium, major ions, right? And I think you can predict that. I think groundwater age should be one of the major predictors, right? Especially with reactions that's in disequilibrium, reactions that take forever. Because we have the spectrum of age from modern to thousands of years. I was imagining the possibility of predicting how much, say, calcium there should be down to 1 kilometer. If you just say because we know this aquifer has carbonates mostly. This aquifer has, it's basaltic, and you know the mineralogy of that. Without doing freaky calculations, you can just do ratios with, uh, you know, the reaction constants. I was more keen on that, but I think for the anthropogenic tracers, sure, you can, or contaminants, you can apply that too. But
Andy Manning, who was a PhD
yeah,
here
yeah,
for the Salt Lake Valley aquifer,
mm-hmm. Yeah, uh-huh.
found that our definition of modern is a little bit slightly different.
Sure. Yeah.
Here, at least in the Salt Lake
Uh-huh.
Valley,
Is contaminated. Yeah.
Yeah.
Or there's a signal. There's a signal, right?
Yeah.
Yeah. What's a little caffeine in your groundwater? That's helpful. Wow. Wow. Cool.
And actually,
I see.
about virtually 0% of the water that we
Mm-hmm. Oh. Yes, Isaku. Mm-hmm.
calculated.
Mm-hmm.
Value.
Sure. Yeah. Uh-huh. Yeah. Yeah. Right. Huh.
How is that? What degree is that?
Well, the difference there is there's the river flux, and a big unknown is the groundwater flux. There's actually groundwater discharging to the ocean, right? And that's something I know a few people, some groups are working on that. We actually have global maps of groundwater discharge to the oceans. So it's just a matter of connecting that to solute load, meaning concentrations. Um, I think that's an even simpler, more direct calculation. You don't need to go through age. You just find all the wells that are close to the coast and multiply the concentration by the flux. But I don't know well, let me put it this way. Actually, I talk about this in one of my other talks. I know it for nutrients. For example, groundwater discharge is about 1% of river discharge to the ocean. But in terms of nutrients, it's about 50%. I don't know about solutes, but nutrients meaning nitrogen, etc. So when you think about, all Mississippi is dumping nitrogen to the Gulf of Mexico, well, guess what? Groundwater can be half of that. Yeah. But I think that part, you can skip age. I think age is a way of getting at things you might not be able to normally estimate, or it gives you a guess at the starting point. Yep, Sarah.
Yeah, you talked about which
Mm-hmm.
question of it all.
Yes, sure. No, but in this case, recharge is already P minus E implicitly, right? And yeah, it was all empirical, right? We know rainfall, we know recharge, but recharge is implicitly P minus E. So if the recharge is changing, we don't know if it's change in P or a change in E, really, in that correlation. Yeah, but that's a good point. It could change. It's it's uncomfortable doing that. That's why it's like, no, let's not even go beyond the LGM. We're already stretching quite a bit here. Um, I think what should be somebody's postdoc or PhD is to run those models with a real hydrologic model and do P and E and recharge. That'd be something for the community, right? And 15 years ago, that was supercomputing stuff that only NCAR could do. I think nowadays you just need somebody with access to a big enough computer. Well, I'm exaggerating, but I think it's doable nowadays with modern computing and the models we have. Yes. Paul.
Have you looked at distribution? I'm thinking of turnover time.
Mm-hmm. Mm-hmm.
And so that's a bulk property.
Yeah.
From modern water.
Yes.
And so have you looked at multiple?
Hmm.
If you're looking at a mathematical
Sure.
modern water turning
Yeah. Yeah.
many times.
Right. Yeah.
Your time scale.
Mm-hmm.
Would you expect
Mm-hmm. Mm-hmm.
again, not putting a
Sure. Sure.
that's an energy flow.
Sure. Uh-huh. Right. What we did not do, because it was really, this was a challenge at the time, this data set was about a terabyte. A terabyte 15 years ago is a lot, right? So it barely fit on commercially available hard drives at the time. So the student was just barely able to make the visualization and calculate things. Kevin, right? He actually has the full spectrum. That's why I told him, Kevin, you can spend a career analyzing this data, especially if you go into water rock interactions. But he moved into other problems. The reason I bring that up is he or somebody else could easily do the sensitive analysis with the data we have right now. In fact, nowadays, I would just do a simple machine learning analysis on that, do random forest, and it'll tell you what's really dictating what. You could do that nowadays, but he's like, I don't even know if the hard drive will still connect to my computer because it's like this old connector sort of thing. But yeah, that's a good point. But I would caution that though, because of the so much simplification went into our analysis. You really can only go down so many levels in terms of details. Going back to the Mona Lisa mosaic analogy, right? I think we don't want to overread it because there's already a lot that went into just creating that the calculations and the simplifications. Um, but so I like models like that, but I'm also a brute force kind of modeler. So nowadays I would just, let's just do some brute force models, a real 3D model that's still not quite 3D stratigraphy, but has a little bit more complexity if we wanted to dig deeper into these things, right? There's been groundwater flow models for CONUS, for example, like what Reed Maxwell does. But this predated that work. So now I would do that instead. And then you can still use some more sophisticated tools to extract insight like machine learning. But I would say the biggest thing from what my student Kevin told me is really just the water table slope, which is duh. It makes sense. But you can do it's all Darcy's law in the end. But he said the biggest sensitivity was water table slope.
Building on that, do you have a sense for how much?
So that's a good point, Gabe. In this case, this was all natural conditions, no pumping. right? So it's to the extent that those water table maps that we use to parameterize our parameter space includes pumping. But I don't know. I don't remember now what Ingfan did, if she was actually taking that into account. And remember, we're doing it, the flow field is steady in our calculations. So those have changed through time. Of course, there's seasonal changes, but pumping should change those, and changes in ET should be changing that, even I think in human timeframes. None of that was in our calculations because we wanted to create the Mona Lisa with no ears.
Well, great.
Thank you.
For
Yeah, thanks for having me.